Hello and welcome to today's video. Today we are going to see a few examples of vector spaces. Now I'll go through most of these examples pretty quickly without going too deep into the technical details, as mostly we will not deal with vector spaces on that level, but rather we'll deal with subsets of vector spaces that we already know. This will be a topic in the upcoming videos, but for now let's have a look at some vector spaces. One prominent vector space, of course, is R to the n. We've already talked about this, and this will actually be the most important one for this lecture. But in this example, I'd like to have a look at a more exotic vector space. And I'll start with a simple one. I'd like to define the following set. I'll call that V. So these are going to be the vectors in this example. And the vectors are going to be functions. I'll use functions from the reals to the reals. And those functions will have the form f of x equals m times x plus t, where m and t are parameters, constants in the reals. So what this is, something that is known as the set of affine linear functions on R, or sometimes you can just say linear functions, but technically that's not quite correct. And we learn about this later on. So those are affine linear functions on the reals. And now to make this into a vector space, we'll have to define the necessary operations. So we'll start with the addition. We want to define an addition. So let's say we have two functions, f and g. And let's say f is of the form mx plus t for some m and some t. And g is of the same form, but the m and the t might be different. So let's say we have m bar and t bar. Yeah, so mt is in R here, and m bar t bar is also in R. Then how do we define the sum of those two functions? So we need to define f plus g. The result is again a function that maps from R to R. And then we need to define how that function maps any given input vector or input scalar x, And what we do here is we just add the two functions pointwise. And that yields m plus m bar times x plus t bar. So that is, by our definition, the sum of those two vectors, those two functions here. And now, of course, we have to look whether the axioms of vector spaces are actually fulfilled here. The first axiom is the neutral element. So is there a neutral element with respect to this operation? And that neutral element is then also a function, of course. And that function will just take on the form n of x equals 0. So the parameters m and t are both 0 in this case. That means n is actually in that class of functions that we are looking at. And if we add this 0 function to any other function, it doesn't change the function. So that is actually a neutral element that does exist. What about the inverse? Let's say we have a function f of x, of the form mx plus t, and we want the inverse of that. Well, the inverse minus f is then simply the function minus m times x plus minus t. Because if we add those two functions, this one and this one, using this definition of addition, then the result is 0 times x plus 0, so we get our neutral element n. And then we also have to care about associativity and commutativity. Both axioms are fulfilled in this case. I won't do the computations in detail. Basically, it just boils down to adding real numbers. What we do in effect is adding the m's and adding the t's, and of course addition in the reals is associative and is commutative, so that also is inherited by this definition of function addition, right? So this addition is associative, and it also is commutative. So addition works. What about the scalar multiplication? We also need to define that. So given some lambda in R, and given some f of the form mx plus t, we need to define what we mean by the new function lambda times f. Again, that is a function from R to R, and we define that function through definition of how it acts on any given input. So lambda times f of x, and again we just do this pointwise. So what we do is we take lambda times m times x plus lambda times t to be the new function, the result of this scalar multiplication. And again, we'll have to look at the axioms here. Let's first see what the neutral element is of scalar multiplication. Well, that is easy, of course. It's just setting lambda to the real number 1. That's the neutral element, because 1 times m is m and 1 times t is t. So if lambda is 1, then 1 times f is just the function f itself again. That definition also yields an associative operation, which can easily be verified. Again, that boils down to associativity of the real numbers. And the distributive laws also hold. And again, that's a little technical, but you can just verify it by doing the computations, and it all boils down to the distributive laws in the real numbers once again. So these pointwise addition and scalar multiplication actually lead to a vector space. So this space of affine linear functions is a vector space. Now that was a somewhat abstract, but still hopefully pretty simple example. I'd like to quickly discuss a generalization of that we will encounter sometimes. And it works in the same ways. So instead of just using affine linear functions, we could extend that idea to using polynomials. And that's something that we will sometimes have to do. We consider polynomials of a given maximum degree. And we'll define that set pk to be all polynomials of degree at most k. So that is the set of all polynomials with coefficients in R and degree at most k. Formally, pk can be written as the set of all functions p from R to R, where px is of the form sum from 0 to k lambda I times x to the I. And those lambdas are the coefficients, so lambda 0, lambda 1, and so on, up to lambda k are real numbers. So that is a set of all polynomials of degree at most k. And that is a vector space. The reasoning is the same as above, and as you have already guessed, hopefully this even contains the more special case of affine linear functions. That is simply the case k equals 1. So an affine linear function is a polynomial of degree at most 1. So that set of affine linear functions is P1. Okay, so I'm not going through the details here once again. It's the very same reasoning. Let's have a look at one different example, one more geometric example here, and one that we'll also meet later on. Part C. Let's define the set V as all multiples of a 2 tuple. So lambda times 2 minus 1. Take any fixed vector, basically would do the same here. 2 minus 1 is just a simple example. We take lambda times that and then lambda in R. So that is a subset of R2, obviously. Geometrically, what this looks like is something like this here. So you have that vector 2 minus 1. It's this vector here. And then we just scale that. So we multiply that by some scalar lambda, and that means the vector becomes longer or shorter. So longer if we have lambda greater than 1. We'll do something like this. Or shorter, we might end up something here if we do a lambda between 0 and 1. And of course we can also use negative lambdas, and that just would flip the direction. So this line also extends here, right? So this is that set V here. That's a line through the point 0 in direction 2 minus 1. And now we can of course ask, is this a vector space? Well, we would have to equip it with an addition and a scalar multiplication once again. And we can easily do this by just taking the definitions from R2. So what we want to do is vector addition and scalar multiplication are defined as in R2. And that means those operations already inherit all the properties from R2. And we know that R2 is a vector space. So of course, those operations will have the desired properties, right? So the desired properties are inherited from R2. The only open question here is, if we apply the operation to vectors in V, will the result actually be in V? Or will it be somewhere else? We could end up somewhere in R2, will surely be in R2, but maybe not in V anymore. So that is basically the only point we'll have to care about. If the operations actually keep us in that set V, then V surely is a vector space, because all the nice properties of the operations are inherited from R2, from the larger vector space. So we only need to ensure that applying vector addition and scalar multiplication to elements of V yields an output in V. And then we know that we have a vector space. So let's try to do that. Let's start with addition. So let's say we have two vectors a, b that are contained in V. That means there is lambda 1 in R with a equals lambda 1 times 2 minus 1. A is in V, so it must have that form for some lambda. So we know there is a lambda such that we can write A in this way. And of course the same is true for for B, sorry. So there is some lambda 2 in R such that B equals lambda 2 minus 1. So the question is, what about A plus B? Where A plus B is, A is lambda 1 times 2, lambda 1 times minus 1, and B is lambda 2 times 2 and lambda 2 times minus 1. So that here is lambda 1 plus lambda 2 times 2 and lambda 1 plus lambda 2 times minus 1 by definition. So what we get is lambda 1 plus lambda 2 times 2 minus 1. And that factor here is lambda 1 plus lambda 2. That is contained in the reals. So that means A plus B does have the form required for being in V. So that confirms that this vector actually is contained in V. Right? That means the sum of two vectors stays in V. Sum of two vectors from V stays in V. One could also say V is closed with respect to vector addition. Okay, so that settles the question for the vector addition. Let's have a look at scalar multiplication. What about that? Well, again, we need an A in V. And that means there is a lambda 1 in R with A equals lambda 1 times 2 minus 1. And we just take a lambda in R. And the question is, what about lambda times A? Is that again contained in V? So does it have the form that we require? And the answer is almost as simple here. So what we get is lambda times A is the same thing as lambda times lambda 1 times 2 minus 1. And here we have a product of two real numbers, lambda times lambda 1. So of course that is in R again. So that means this result here is once again in V. Okay, so the vector space V is also closed with respect to scalar multiplication. Okay, and again, the nice properties of scalar multiplication are inherited from R2. So we can be sure that V actually is a vector space then. One last example. We'll just modify that last example a little. And we'll define V as 1, 0 plus lambda times 2 minus 1 lambda in R. So we just add a constant vector to what we have seen before. Well, the geometry of this, how does that change? Basically, we have this point 1, 0, that is here. And then again, we have this vector here that points in this direction, that way. So this is our vector 2 minus 1 plus 1, 0. Here's 1, 0. Here's 1, 0 plus 2 minus 1. And then, of course, we would not just add 1 times 2 minus 1. We could also add scaled versions. And if we do this, that line either extends in that direction, or we move back here somewhere, or we could also reverse the direction, move outwards like this. Yeah. So that would be our vector space, or supposedly vector space V. Now, if you look at that geometry here, you should immediately see a problem. And that problem is, what about the neutral element of addition? Again, this is a subset of R2, and we just want to use the operations that we know from R2, like we did before. And that means we need to make sure that the neutral element of addition is contained. Now that is the 0 vector, but apparently the 0 vector is here. Now that is not contained in our space V. So consequently, that set here can never be a vector space because it does not contain the neutral element of vector addition. So V does not contain the neutral element 0, 0 of vector addition. And therefore V is no vector space. Okay, so a seemingly small change can make a big difference in this vector space property. Now, in the upcoming video, we'll expand a little on that idea that we've visited in C, and later we'll also expand on the idea we've visited in D, because D, well, it's not a vector space, but it's almost a vector space. Yeah, it's just a constant shift. So maybe it's still useful, and it will turn out that it is useful, of course. But first we'll discuss about the properties of vector spaces that are derived from larger spaces by taking subsets, suitable subsets. And that will be the topic of one of the upcoming videos. I'll see you there.